Imagine, just for a second, you're standing right in the middle of a crowded, incredibly noisy room.
Okay.
Let's say it's a party. It's loud. There are, I don't know, dozens of conversations happening all around you. Glasses are clinking. There's music playing. It's just a wall of sound.
It's a sensory overload situation, really.
Totally.
Yeah.
But you're managing it. You know, you're focused. You're deep in a conversation with a friend, and somehow your brain is filtering everything else out. All that background noise is just a hum.
Right.
But then from across the room, someone says your name. Or maybe a glass shatters on the floor, and instantly your focus just snaps.
Yeah, your attention is completely redirected.
Exactly. Your friend's face just fades out, and that specific sound becomes the most important thing in the world. That mechanism, that sudden automatic switch in your brain that decides this matters right now, that is what we are digging into today.
And it's maybe one of the most fundamental jobs the brain has. Because you think about it, the world is just infinite in its detail.
Right.
The amount of data coming in at any 1 second is completely overwhelming.
Yeah.
But our attention, our focus,
Yeah.
that's a finite resource.
Very finite.
So we have to filter. We have to prioritize. And the system that's responsible for that filter, for deciding what gets through the gate and what gets ignored, is called the Salience network.
The Salience network, I love that name. It sounds authoritative, like it knows exactly what it's doing.
It does, most of the time.
And today we are doing a massive deep dive into this system. We're going to unpack its anatomy, its history, which it turns out involves some really fascinating drama in the neuroscience world and its absolutely crucial function. And we have a stack of 3 really incredible papers to guide us.
We do. And what's so exciting about this particular stack is that it tells a story. It's an evolution in our understanding. We're not just looking at a static map of the brain here.
So where are we starting?
We're starting with a retrospective by William Seeley from 2019. It's titled The Salience Network, a neural system for perceiving and responding to homeostatic demands. And this one looks way back at how the network was first discovered, which was actually in the context of dementia research.
Okay, so the origin story, then where do we go?
Then we jump to a major review from 2023. This one's by Schimmel-Fenning and a team of colleagues, and it's called The Role of the Salience Network in Cognitive and Affective Deficits.
And this one is about what happens when it breaks.
Exactly. This is the paper that breaks down how this network fails in a huge range of mental disorders, everything from anxiety to schizophrenia.
Wow.
And then we're capping it all off with something that's basically hot off the press, a 2024 paper by Kosakowski, Eldafe, and Buckner.
Oh.
It's titled Ventral striatum is preferentially correlated with the salience network, including regions in dorsolateral prefrontal cortex. This uses some really cutting-edge precision imaging that redefines what we know about the brain's reward system and how we might actually treat depression.
So we're going from the discovery of the network to understanding its role in disease and then finally to potentially fixing it.
That's the journey.
Yeah.
From anatomy to pathology to therapy.
It's a journey from the very mechanics of who we are socially to how we break and then to how we might actually fix the machinery. So let's rewind. Let's go all the way back to the beginning.
Let's do it.
Because when I was reading that first source, the Seeley paper, I was really surprised to learn that this network wasn't just, found on a map one day. It came out of a real scientific controversy.
It absolutely did. And to really get that, we have to set the scene. We're talking around 2003 at the University of California, San Francisco.
Okay.
Now, at this point in time, functional MRI, fMRI, is the biggest tool in neuroscience. I mean, everyone is using it.
Yeah.
But the standard way of doing things was task-based fMRI.
Which means you put someone in the scanner and you give them a specific job to do.
Exactly. You tell them, tap your finger every time you see a red circle, or look at this picture of the spider and tell us how you feel.
Stimulus equals response.
Very controlled, very tidy. You look at what parts of the brain light up with oxygenated blood when they do the task. But there was this kind of rogue methodology emerging at the time called resting state fMRI.
Which is pretty much what it sounds like, I'm guessing. You put them in there and tell them to do absolutely nothing.
Precisely. The instructions usually something like, lie as still as you can, keep your eyes open, stare at this little crosshair on the screen, please don't fall asleep, and try not to think about anything in particular.
Which is impossible.
It's impossible, but you try, and you just measure the slow, spontaneous fluctuations of blood flow in the brain while it's idling.
And looking back at the Seeley paper, he makes it really clear that at the time, this was not a popular idea.
Yeah.
He actually uses the word voodoo. Some people just thought it was noise.
Voodoo is a good word for it. Or magic, or just bad science. Because think about it from the perspective of a really rigorous, old-school scientist in 2003. If you aren't controlling the input, the stimulus, how can you possibly trust the output? If the person in the scanner is thinking about their grocery list or an argument they had with their spouse or that their nose itches, isn't that just creating random junk in the data?
Yeah, you have no control variable.
None. They thought the signals were just physiological artifacts. Their breathing, their heart rate, maybe just the scanner itself drifting. They thought it was meaningless noise.
But Seeley, who was a neurologist, he saw something else in that so-called noise.
He did. He was one of the people who saw a revelation. He saw patterns. He and others noticed that even when you're not doing anything, certain parts of the brain fluctuate together. Their activity rises and falls in perfect synchrony.
They're connected.
They are functionally connected.
Yeah.
It suggested that there are these intrinsic hardwired networks that are always on, always humming in the background, basically maintaining our baseline reality.
And Seeley wasn't just looking for networks for the sake of it. He had a very specific clinical puzzle he was trying to solve. He was working with patients who had frontotemporal dementia.
Specifically, the behavioral variant of frontotemporal dementia, or BVFTD. And we really need to distinguish this from Alzheimer's disease.
Right, because when most of us hear dementia, we immediately think of memory loss.
Exactly. Grandma forgetting where she put her keys or repeating the same story over and over. That's typically Alzheimer's. It attacks the parts of the brain responsible for memory, the what and the where of your life.
But BVFTD is different. It's not about memory, is it?
No, it's so much more insidious.
Yeah.
BVFTD attacks the who. It fundamentally steals your personality.
That's terrifying.
Seeley describes these patients in the paper, and it's just heartbreaking. They lose their social grace. They lose tact. They might walk up to a total stranger and say something incredibly offensive because that internal filter is just gone.
So they lose their empathy.
They lose empathy. They lose insight into their own behavior. But here's the really weird part, and this is the clue that Seeley picked up on. It's not just the social stuff.
Oh.
They also lose their drive, their motivation. They become profoundly apathetic. They might just sit on the couch all day, not wanting to do anything. And even stranger than that, they become insensitive to their own physical signals.
What do you mean by that?
Well, they might not complain if they're in a lot of pain. They don't seem to care if they're freezing cold or dangerously thirsty.
Yeah.
The internal alarms just aren't going off.
Wow, okay, so the brakes on their social behavior are broken. They say inappropriate things.
Right.
The gas pedal for motivation is broken. They have no drive. And the dashboard sensors for their own body are broken. They're almost numb to their own physical needs.
That's a perfect way to put it. And so Seeley asked this brilliant question, the kind of question that really launches a career. What single system in the brain, if it were to break down, would explain all of those seemingly disconnected symptoms?
Because they do seem so different. Why would losing your empathy and not caring that you're cold be related at all?
They seem like they should be in totally different departments in the brain, right?
Right.
One is complex social emotion, the other is basic survival sensation.
Right.
Unless they're actually part of the same processing loop. Unless the ability to feel a social emotion is actually built on the same scaffolding as the ability to feel your body.
Okay, I see where this is going.
And this leads to the big aha moment. It's 2004. Seeley goes to a lecture by an evolutionary biologist named John Allman. And Allman isn't talking about dementia. He's talking about these very specific, very strange brain cells called von economoneurons, or VNs for short.
VNs, right. I remember this from the reading. These are the really big spindle-shaped neurons.
Yes. And in neuroanatomy, shape almost always tells you something about function. These neurons are what we call layer 5 projection neurons. They are huge, and they're shaped like spindles, which strongly suggests they're built for speed.
They can send signals really fast over long distances in the brain.
Very, very rapidly. And here's the kicker. They aren't in every animal. They're evolutionarily very recent. You only find them in great apes, humans, cetaceans, so whales and dolphins, and elephants.
So animals that have really complex social structures.
Exactly. The kinds of animals that need to process subtle social cues incredibly quickly. If you're a dolphin or a human, navigating your social hierarchy is just as important for survival as finding food. You need high-speed hardware for that job.
So Allman is up there talking about these specialized social neurons.
Right. And then he points out that in the human brain, these VNs aren't just scattered everywhere. They are highly concentrated in two specific spots. A region called the anterior cingulate cortex, or ACC, and another called the frontoinsular cortex, or FI.
Location, location, location.
Precisely. And Seeley is sitting there in the audience looking at Ullman's slides of the brain, and he has this realization, wait a minute, those two spots, the ACC and frontoinsula, those are the exact areas that are withering away in my frontotemporal dementia patients.
That is just such a cool scientific moment. The light bulb just goes on over his head.
It's a perfect example of scientific convergence. He hypothesizes that this specific disease, BVFTD, is essentially a VENopathy. It's a disease that specifically targets these big, fast social neurons.
And when those neurons die, the whole network they form just collapses.
And since that network is the bridge between sensing what's going on in your body and navigating the complex social world, the patient loses both abilities at the same time. The puzzle pieces fit.
So he goes back to the lab, he uses this voodoo resting state fMRI on healthy people, and he basically plants a virtual seed in that frontoinsular cortex to see what it's connected to.
And boom, the map just lights up.
Yeah.
He found that the anterior insula and the anterior cingulate are incredibly tightly coupled. Even when you're just lying there daydreaming, they're constantly whispering to each other. They form a dedicated intrinsic system. And that was it. The Salience network was officially identified.
Okay, so let's really unpack the anatomy here, because if you understand the parts, the function makes so much more sense. We have these two main hubs you mentioned, the anterior insula and the anterior cingulate.
The two core nodes.
In the Seeley paper, he breaks it down into afferent and efferent. So let's start with the afferent one, the input. That's the anterior insula.
That's right. Think of the anterior insula, or more specifically the frontoinsular cortex, as the afferent hub. Afferent just means it receives signals. It's the brain's great integrator.
What's it integrating?
Pretty much everything that's happening inside your biological suit. It receives all the visceral and autonomic feedback from your body. Your heart rate, your blood pressure, how full your bladder is, the distension of your gut, the temperature of your skin, pain signals, an itch, a tickle.
What's that whole collection of feelings?
It's a sense called interoception, the sense of the internal state of the body. The insula is where you feel yourself from the inside out.
And that directly explains the physical side of the dementia patients, right? They stopped caring about being cold because their anterior insula wasn't getting or wasn't processing the signal that said, hey, body temperature's dropping.
Exactly. The dashboard was dead. But the insula does something even more incredible, and this is really the magic trick of human consciousness.
Okay.
It integrates that raw physical feeling with the environmental and social context you're in. It takes the physical sensation of my stomach is churning and my heart is racing, and combines it with the external context of I am standing in front of an audience of 500 people.
And it creates the subjective feeling of anxiety.
Precisely. Or it takes the sensation of my face is flushing with heat and combines it with the context of I just told a really bad joke at a dinner party, and it creates the feeling of embarrassment.
So it's the place where raw sensation gets translated into a named emotion.
That's the model. In this view, emotion isn't some ethereal spiritual thing. Emotion is the brain's cognitive interpretation of a body state within a specific context. The insula is where that translation happens.
That's a huge idea. Okay, so now we feel something. We feel anxious or cold or embarrassed or hungry. The insula has done its job. What happens next?
Now you need to do something about it. And that's the job of the efferent hub, the anterior cingulate cortex, or ACC. Efferent means output.
So this is the action part of the network.
Exactly. The ACC is responsible for generating the response. It communicates with the motor centers, with the spinal cord, with the high-level cognitive centers. It's the part that says, okay, we're feeling anxious, so let's start rehearsing our opening lines.
Well, we're cold. Let's find a jacket.
We're embarrassed. Let's apologize and change the subject. It orchestrates the behavioral, cognitive, and visceral action plan to deal with the feeling the insula just generated.
So it's a complete loop. The insula perceives the homeostatic need, gives it emotional weight, and then the cingulate orchestrates a response to bring things back into balance.
It's a constant dynamic feedback loop. And Seeley actually notes in the paper that he originally toyed with, calling it the homeostatic relevance network.
That's a mouthful.
It is, but it's technically more accurate. Fundamentally, its job is to keep the organism in a state of balance.
Salience network is definitely a lot catchier.
It is. And salience really captures the essence of its higher level function perfectly. Salience just means prominence or importance. This network's job is to identify what is most biologically or cognitively relevant in the environment right now.
It's the thing that separates the important signal from all the background noise.
That's its job.
Yeah.
Which brings us right back to your cocktail party example.
Yeah.
The wall of sound is just noise until the Salience network tags the sound of a breaking glass as important. Pay attention.
And it forces you to look. It overrides whatever else you were doing.
It has to, because that sound implies a sudden change in the environment, a potential threat, or something that requires your immediate assessment. The network says, stop your current conversation, orient yourself to that sound, assess for danger, and then decide what to do.
It's just incredible to think that this specific loop is running constantly every single second of the day, completely below our conscious awareness.
It is the background operating system of your engagement with reality. And this leads us perfectly into our second source, the 2023 paper by Schimmel-Pfennig and his colleagues, because they take this anatomical loop and they plug it into a much bigger model of how the entire brain works, what they call the triple network model.
Yes, I found this part really helpful for visualizing how the brain manages its resources. We're not just talking about the Salience network in isolation anymore.
No, you can't.
We're talking about it as a manager of other equally important networks.
That's exactly right. The Schimmel-Pfennig paper argues that you really can't understand brain function, or more importantly, brain dysfunction, without looking at the dynamic interaction of what they call the big three. So let's meet the players.
Okay.
Network one. The default mode network, or DMN.
This is the me network, right? The one that's on when you're just spacing out.
Yes. This is the network that Seeley and others first noticed turning on when people were in the scanner doing nothing. The DMN is active during rest. It's involved in daydreaming, in autobiographical memory, thinking about yourself, worrying about the future, reminiscing about the past. It's your internal world.
When you're lost in thought in the shower, that's your DMN, hard at work.
That's a perfect example. Okay, so that's network one. Network two is the frontoparietal network, or FPN. It's also sometimes called the central executive network.
And this one is the opposite, right? This is the task network.
It's the task world. The FPN is active when you are actively engaged with the outside world, solving a math problem, navigating a map, learning a new skill, focusing on a speaker. It's all about external, goal-directed tasks.
So DMN is internal world, daydreaming. FPN is external world, working.
Right. And here's the crucial part. Generally speaking, these two networks are anti-correlated.
Meaning when one is on, the other one should be off.
They should be. You can't effectively solve a complex calculus problem if you're simultaneously busy ruminating on an embarrassing thing you said in high school. You need to turn off the internal chatter to focus on the external task.
I feel personally attacked by that example. I do that all the time.
We all do. But biologically, it's inefficient. Your brain is trying to do two opposite things at once. And this is where the Salience network comes in. It's the third network. It is the switch, the dynamic toggle. The Salience network, and specifically that right anterior insula, is constantly monitoring both your internal state and the external world. It detects a salient event, an external threat, a hunger pang, a new instruction from your boss, and it generates a control signal.
And that signal does what?
It does two things at once. It engages the frontoparietal network to handle the incoming task, and it actively suppresses the default mode network to stop the daydreaming and get you focused.
It's like a traffic controller at an airport. It sees an important plane coming in to land, that's the salient event, and it clears the runway and tells all the other planes to circle.
That's a great analogy. It physically shunts the brain's neural resources from one state to another. And the paper points out that the efficiency of this switching mechanism is highly correlated with things like intelligence and good executive function.
So people who can snap between those states, from deep internal reflection to intense external focus quickly and cleanly, they tend to perform better on cognitive tasks.
They do. Their switch is more efficient. But what I found really fascinating, and frankly, a little difficult to wrap my head around at first, in the Schimmel-Pfennig paper, was their discussion of predictive coding.
Yes.
This feels like a level deeper. It's not just that the brain is reacting to stimuli, is it?
No, and this is a really crucial concept in modern theoretical neuroscience. The brain is not a passive receiver. It's not a video camera just recording what's happening in the world.
It's proactive.
It is a prediction machine. It is constantly, from moment to moment, generating a model, what we call a Bayesian prior, of what it expects to happen next.
Okay, so right now, my brain is actively predicting that you're going to finish your sentence in English with a certain tone of voice at a certain volume.
Exactly. Your brain is running a simulation of the next 2 seconds of reality. And as long as I do, in fact, finish my sentence in a normal way, your Salience network stays quiet. Everything is matching the prediction.
It's business as usual. Right. We ignore the hum of the refrigerator because we predict it's going to be there. We ignore the feeling of our clothes on our skin because it's a constant predicted sensation.
But if you suddenly, I don't know, started screaming in the middle of your sentence.
Or if I switched to speaking French. Or if the refrigerator suddenly stopped humming. That would create what's called a prediction error.
Reality violated the prediction.
Yes. And the insula's job is to integrate that bottom-up sensory signal. He just screamed with the top-down prediction. He was supposed to be speaking quietly, and it calculates the difference between the two. That difference, that error signal, is salience.
So salience is just another word for surprise.
It's the neural signature of surprise. It's the brain screaming, update the model, something unexpected just happened, pay attention to this.
That makes so much sense. We only notice things when they deviate from the established pattern. The salience network is basically the brain's anomaly detector.
Precisely. It's an incredibly efficient system. It minimizes the energy we spend processing the mundane and the predictable, so we can focus all our resources on the surprising and the new. Now, here's the critical part.
What happens when that mechanism goes wrong?
What happens if that prediction error calculation goes haywire? That is the core of what they call the triple network model of psychopathology.
This was the heaviest part of the Schimmelpfennig paper for me. It basically argues that you can frame almost every major mental disorder as some kind of failure in the balance between these three networks.
It's a very powerful framework.
So let's unpack the hyperactive side first.
Yeah.
What happens when the salience network is too loud or too sensitive?
If the salience network is hyperactive, it means the threshold for what your brain considers important or threatening is set way too low. This is the core mechanism of anxiety and neuroticism.
So a weird look from a stranger on the Singway isn't just a weird look. The salience network flags it as a potential threat.
Yes. It generates a massive prediction error for a very minor event. It flags it as highly salient. It engages the body's stress response, the racing heart, the sweaty palms.
And it hijacks your attention.
It does. And because it's hyperactive, it also can't do its job of effectively turning off the default mode network. So you get this toxic combination of hypervigilance, constantly scanning the world for threats and rumination, constantly worrying about yourself and the what-ifs.
You're stuck in a loop of, I am in danger, and what if something bad happens?
Exactly. The paper also mentioned PTSD as a classic triple network failure.
Right.
PTSD is such a tragic example. You have a profoundly hyperactive salience network that is constantly flagging benign things in the environment as mortal threats. A car backfiring isn't just a noise, it's a gunshot.
The prediction error is dialed up to 11.
All the time. But at the same time, you often have a hypoactive or underactive connection to the frontoparietal network, the executive control center. So you perceive the threat, but you can't cognitively regulate the response. You can't use logic to tell yourself, it's okay, that was just a car, I'm safe now. The brain gets stuck in a state of pure, raw threat detection.
And what about chronic pain? That was another example they used.
Chronic pain is fascinating because you actually see structural changes in the brain. The paper notes that in patients with chronic pain, there's often increased gray matter volume or altered connectivity in the insula itself.
Wait, hold on. The brain physically grows more tissue to feel the pain better.
In a sense, yes. The pathways become more well-trodden. Pain is the ultimate salient signal, right? It's your body's check engine light. If you have chronic pain, the salience network is just screaming 21247. It refuses to ignore the signal.
So it prevents you from focusing on work.
And that's the FPN.
Or from relaxing and thinking about other things.
That's the DMN. The alarm of the pain signal takes priority over everything else. The network essentially reinforces itself to become better and more efficient at feeling the pain.
That is just terrifying. Okay, so that's all about too much signal. What about when the signal itself is aberrant or just wrong? The paper goes into a lot of detail on schizophrenia here.
Yes, this is the aberrant salience hypothesis. It's one of the most compelling theories in all of psychiatry.
How does it work?
So in schizophrenia, it's thought that you have chaotic, dysregulated discharges of the neurotransmitter dopamine, especially in the striatum. Now, dopamine is the chemical that often tags things in the world as salient or valuable.
So normally dopamine fires when I see a delicious piece of cake or I see a good friend or I achieve a goal. It tells my brain this is important.
Right. It says, pay attention to this is valuable. But in schizophrenia, the dopamine system might fire randomly without any relevant trigger. So imagine you're sitting in a room, there's the background hum of the refrigerator, or a random meaningless thought just pops into your head, and at that exact moment, boom, A huge random dopamine discharge happens. The salience network receives that signal and says, that sound, that thought, it is critically, profoundly important.
But there's no actual importance. It's just a fridge. It's just a stray thought. So the brain has to, what, invent a reason for why it feels so important.
Exactly. The human brain is a meaning-making machine above all else. It hates an unexplained feeling of significance. So if the salience network is screaming at the conscious mind, this background static is the most important thing in the world, the conscious mind has to come up with a story. It says, why? It could be just static. Maybe. Maybe it's a coded message. Maybe it's the CIA broadcasting secret instructions to me through the electrical wires.
And that is how a delusion is born. It's the cognitive mind's attempt to explain the feeling of aberrant importance being generated by the biology.
That's the theory. It's a false inference, driven by a failure of the sensory gating system. The filter's broken, but in a way that assigns profound meaning where there is absolutely none.
And then on the complete flip side of that, you have autism spectrum disorder, or ASD. The paper describes this as more of an underconnectivity issue.
Right. In ASD, one of the leading theories suggests that the salience network may fail to tag social stimuli as being particularly salient.
So things like a face, or a tone of voice, or a social gesture.
Exactly. For a neurotypical brain, those are extremely high-priority signals. We automatically lock onto them. For a brain with ASD, the salience network might not flag them as being any more important than all the other sensory data, flooding in the pattern on the carpet, the flicker of the fluorescent lights, the texture of their shirt.
So the switch doesn't flip when it's supposed to. The important social signal gets lost in the noise of all the other sensations.
It can. Or, as the paper also discusses, the switch can become too rigid. There's evidence of a lack of flexibility in switching between the DMN and the FPN. This can lead to real difficulty in handling uncertainty or novelty. If the environment changes unpredictably, the salience network struggles to reroute the brain's resources, which can lead to distress and a strong preference for sameness and routine.
It's just amazing how this one system, this one simple-sounding loop between the insula and the cingulate can manifest in so many profoundly different ways when it malfunctions.
It really is the fulcrum of mental health.
Yeah.
If that balances off, the whole system just tips over.
Okay, so we've established the history, the anatomy, and the dysfunction. Now I want to move to our third source, the 2024 paper by Kosakowski, Eldife, and Buckner. Because this feels like we are taking a microscope and zooming way, way in.
We are. The first two papers were about the big picture of the networks. This paper is all about precision, and it tackles a huge, long-standing problem in neuroscience, the ventral striatum.
The ventral striatum. Okay, so this is deep in the brain, right? Part of the basal ganglia.
Yes. And it includes the very famous nucleus accumbens. This is what people colloquially call the reward center of the brain.
Right. Motivation, addiction, pleasure. This is the part that lights up when you win at poker or eat a piece of chocolate.
That's the one. But here's the problem from a research perspective.
Yeah.
It is notoriously difficult to get a clean image of.
Why is that? Is it just too deep in the brain?
It's deep, it's small, it's anatomically heterogeneous, but the real problem is air. It sits right above your sinuses.
Okay.
In an MRI scanner, the interface between brain tissue and an air-filled cavity creates what's called a susceptibility artifact.
Okay.
It literally distorts the magnetic field in that local area. It causes the signal to drop out or get smeared. It's like trying to take a high-resolution photograph through a foggy, cracked window.
So for years, our pictures of this incredibly important area of the brain were just blurry.
Blurry is a good word for it. And Kosakowski's paper argues that because of this blurriness, previous studies, especially big group studies, where they averaged the scans of hundreds of people together to try and smooth out the noise, made a fundamental mistake.
What was the mistake?
They concluded that the ventral striatum was part of the default mode network.
The daydreaming network. That seems really odd for a motivation and reward center. Why would the go-get-it part of the brain be functionally connected to the lie around and think about yourself part?
It never made a lot of functional sense. And Kosakowski argues it was just plain wrong. He suggests that because the ventral striatum is physically very close to another structure called the subgenual anterior cingulate, which is a core hub of the default mode network, the signals just bled together in those blurry group average scans.
So how did they fix it? How do you wipe the fog off the window, so to speak?
They used a technique called precision functional mapping. And the logic is simple but powerful. Instead of scanning 100 different people one time each, they scanned a few individual subjects, they call them S1 and S2, over and over again, 31 times each in this case.
31 separate MRI scans on one person. That is a lot of time in a very loud tube.
It is an immense amount of dedication. I don't know if you've ever been in an MRI machine, but it is loud, it's claustrophobic, and it's boring. But the payoff is huge. By scanning one person that many times, you can average out the noise for that specific individual and get an incredibly high signal-to-noise ratio.
So you can map the brain of a single person with exquisite detail, respecting their own unique anatomical folds, rather than smearing them into a generic group average.
That's it, exactly.
Yeah.
And when they use this midnight scan approach, as it's sometimes called, what do they find?
The moment of truth.
They found a double dissociation that basically rewrites the textbook. When you look with high precision, the ventral striatum is absolutely not part of the default mode network. It is preferentially and strongly correlated with the salience network.
So the reward center is hardwired to the salience network.
Yes, it forms a very specific corticobasal ganglia loop. The ventral striatum, specifically the nucleus accumbens core, links directly to the anterior insula and the anterior cingulate, which makes total functional sense.
Of course it does. Salience is about what matters. Reward is about what is valuable. They should be talking to each other.
They are the motivation engine and the attention engine. They have to be connected. But the paper goes even further. It distinguishes the ventral striatum from a neighboring region called the ventriputamen.
Okay, now we're getting really granular. These are tiny structures right next to each other.
They are. But this is why the precision is so important. In the old blurry scans, these two regions might have just looked like one big blob. But Kosakowski's team shows they are functionally distinct. The ventral putamen, right next door, links to a different network.
Not the salience or default mode.
No, it links to a network called the cingulo-opercular network, or CoOP network.
Wait, remind me what the CoOP network does again.
It's a task maintenance network. It's the system that helps you stay on task, maintain a rule set over time, and power through fatigue or distraction.
So what you have is the salient system for identifying the new important thing anchored in the ventral striatum,
Right.
and the HAS maintenance system for sticking with the current thing anchored right next door in the ventral putamen.
Yes. The striatum beautifully preserves the distinct network boundaries that are found up in the cortex. It's this elegant biological mirroring. The deep brain structures respect the organization of the surface.
Okay, I get the anatomy. It's really elegant. But here's where I want the so what. The paper connects all of this to the DLPFC, the dorsolateral prefrontal cortex. This is where it gets clinical.
This is the payoff, absolutely. The DLPFC is the part of your prefrontal cortex right behind your forehead. It's traditionally associated with high-level thinking, working memory, and the frontoparietal network. But Kosakowski's precision mapping found something really surprising there.
What did they find?
They found that the salience network has a tiny, specific outpost inside the dorsolateral prefrontal cortex.
So if you imagine the prefrontal cortex is a country, we usually think it's all ruled by the executive network, but you're saying there's this little embassy from the salience network sitting right there.
That's a perfect analogy. And not just salience. They found that within the DLPFC, there are these tightly packed, functionally distinct regions sitting right next to each other. One little patch for the salience network, one for the QAP network, and one for the frontoparietal network. They're all neighbors.
And why does that matter so much?
It matters because of how we treat depression. One of the most effective treatments for drug-resistant major depressive disorder is TMS transcranial magnetic stimulation.
Right, where you put a magnetic coil on the scalp and stimulate the brain non-invasively.
Exactly. And for decades, the standard target for TMS in depression has been the left DLPFC. But for a long time, the targeting was really crude. It was based on scalp measurements, like measure 5 centimeters forward from the spot that makes the thumb twitch.
So it was kind of a shot in the dark. That's why it sometimes worked and sometimes didn't.
Because everyone's brain map is slightly different. But more recent research has refined this. It showed that the most effective TMS target is the specific spot in the DLPFC that is most strongly anti-correlated with the subgenual cingulate.
Okay, break that down.
The subgenual cingulate is a part of the default mode network that is often hyperactive in depression. You can think of it as the brain's sadness center. So the goal is to find the spot on the surface that, when you stimulate it, reliably turns down the activity in that deep sadness center.
And Kosakowski is connecting the dots here.
Yes, this is the big proposal.
Yeah.
He suggests that this specific magic spot in the DLPFC, the one that's anti-correlating with the sadness center, is the salience network node.
Whoa, okay. That's a huge link.
Think it through. We just established from their data that the ventral striatum, The reward and motivation center is a core part of the Salience network. Depression is characterized by anhedonia and lack of motivation.
So if you stimulate the Salience network's embassy in the prefrontal cortex,
You are likely sending a signal down through the entire network, modulating those deep brain structures in the ventral striatum. You are, in effect, jump-starting the motivation and reward system that has gone offline in depression.
but because these different network regions, the salient spot, the executive spot, the Kelly spot, are all packed so tightly together in the prefrontal cortex, if your targeting is off by just a few millimeters.
You might be stimulating the wrong network entirely. You might be hitting the cognitive control network instead of the salience and reward network, and that would explain the variability in treatment outcomes.
This is why the average map fails. To be effective, you need an individual precision map to find your specific salience node in your prefrontal cortex.
Exactly. This is the promise of personalized medicine in psychiatry. It moves the field from a one-size-fits-all approach to a truly targeted, network-based therapy. It's no longer about, let's stimulate the general area of the DLPFC. It's about, let's find and stimulate the salience embassy.
Okay, let's step back and just synthesize all of this. We've covered a huge amount of ground here.
We really have.
We started with William Seeley back in the early 2000s, looking at these tragic dementia patients who had lost their social grace and their physical sensitivity. And from that clinical puzzle, he identifies the salience network, the core system that integrates feeling and doing.
We then moved to the triple network model from the Schimmelpfennig paper, seeing the salience network as the brain's great switchboard operator, the thing that toggles us between our internal world of thought and our external world of action.
And we saw how devastating it is when that switch gets stuck, like in anxiety or chronic pain, or when it fires randomly and assigns meaning to nothing, like in schizophrenia.
And we ended with the cutting edge, this 2024 precision imaging from Kosakowski's group, proving that this network is fundamentally hardwired into our brain's reward system. And in doing so, identifying what is likely the crucial keyhole we need to unlock to treat depression more effectively.
It's a really remarkable trajectory of scientific discovery. It transforms the salience network from just being, another blob on a brain map to arguably the most critical system for how we navigate our reality. It literally determines what we care about from moment to moment.
It does. It sets our priorities.
And that leads me to my final thought, and it's a bit of a weird philosophical one, but I can't shake it.
Go for it.
If the salience network is what determines what matters to us, if it's what determines what grabs our attention, what we find rewarding, and what we interpret as a threat,
I think I know where you're going with this.
then to what extent is my reality just a reflection of where my personal salience network decides to shine its spotlight? If my network is tuned differently from yours, if mine is hyperactive and sees threats everywhere, while yours is underconnected and misses social cues, we are literally living in different worlds.
We are. We could be standing in the exact same room at the exact same party, but we are experiencing two completely different realities. We don't see the world as it is. We see the world as our salience network presents it to us.
And if that network is malleable, if it's sensitive to dopamine, sensitive to magnetic stimulation, sensitive to therapy and learning, then our reality itself is malleable too, which leads to the big question, are we just our salience network?
That is the ultimate question, isn't it? In so many ways, the axiom, you are what you pay attention to, is biologically true. And the salience network is the absolute gatekeeper of your attention. So in a very real biological sense, maybe the answer is yes.
Something to think about the next time you hear a glass break at a party. Or, perhaps more interestingly, the next time you don't. Thank you for joining us on this Step Dive.
A pleasure, as always.
We'll see you next time.